Hello, this is Brian Swift, Chemistry 112, 1211K, Section 4. This is the first lecture, and this is the way we're going to be doing things, is I'm going to be reading the PowerPoint presentation and giving additional information as I see fit with each slide. These slides pace our information that we're given and prompt us for the information that we need to work on. And I've got some more insights on some of these that I would like to share with you. So let us begin. So this is what we're going to do. Today we're only going to be looking at 1.1 and 1.2. Chemical substances and processes are essential for our existence, providing sustenance, keeping us clean and healthy, fabricating electronic devices, enabling transport, and much more. So what this is trying to tell you is chemistry is everywhere. You have a cup of coffee, which is a homogeneous solution of brown stuff and sugar, and it's in a porcelain cup that was baked in a kiln from clay. There's soap, which is a salt of a fatty acid, and it's being used to wash your hands. Your body is chemicals. And there's plastic on electronic devices, in this case a remote. And chemicals are involved in energy, what we use to put into our cars, the gasoline. So, in section 1.1, we're going to look at the historical development of chemistry, examples of the importance of chemistry in everyday life, describe the scientific method, differentiate among hypotheses, theories, and laws, provide examples illustrating macroscopic, microscopic, and the symbolic domain. Chemistry is the study of the composition, properties, and interactions of matter. Attempts to understand the behavior of matter extend back more than 2,500 years. The Greeks considered that matter consisted of 4 elements: earth, air, fire, and water, but the table of the elements has expanded much more since then, and alchemists attempted to perform base metals into noble metals, namely lead into gold. And we may laugh at that today, but the alchemists were the chemists of the day. Isaac Newton was considered to be an alchemist. This portrayal shows an alchemist's workshop around 1580. Although alchemy made some useful contributions to how to manipulate matter, it was not scientific by modern standards. Actually, much of alchemical texts is written in terms of Greek gods and planets and stars, and it's highly symbolic language that is poorly understood today. Chemistry is interconnected to a vast array of other scientific, technical, engineering, and math disciplines. It is called the central science, and this diagram shows that it's in the middle of everything. the way I see it, biology started off with basically nomenclature, naming things and categorizing things, and physics gets down to the subatomic particles and forces of nature. And chemistry is central in that regard, between the fields and forces and particles that make everything up, and the large constructs of squirrels and deer and dinosaurs. So knowledge of chemistry is central to understanding a wide range of scientific disciplines. This diagram shows just how some of the interrelationships between chemistry and other fields. Examples of chemistry in everyday life. Actually, everything is chemistry. Anything that involves a substance changing from one thing to another, such as fire, photosynthesis, digesting food, as it says here, the making of clothing, cookware, and anything plastic, and refining crude oil into gasoline. But industry uses chemistry because industry makes things and has to convert something to something else. As you proceed through this course, you will discover many examples of changes in the composition and structure of matter, how to classify these changes in matter and understand how they occur, and the changes in energy that accompany these changes in matter. Chemistry is a science based on observation and experimentation. By the way, it was Galileo that laid the foundations for what we now know as science. He based his theories, getting closer to the truth, on experimentation. Chemists often formulate a hypothesis, which is a tentative explanation of observations. By the way, anything highlighted like this is something you should really commit to memory. So, a hypothesis is a tentative explanation of observations. The laws of science summarize a vast number of experimental observations and describe or predict some facet of the natural world. A theory is a well-substantiated, comprehensive, testable explanation of a particular aspect of nature. So, if you take a hypothesis and you test it, it looks like it's valid, then you may make this a theory. It is your theory that this is the way this thing works. It's supported by this evidence. By the way, another word for observation that comes up occasionally is a fact. So, something's not true. If you say it's a fact, you don't mean it's true, you mean it's an observation. A law is like a theory, but a little bit stronger. It means in all cases that we've observed to date, that theory is supported by the evidence. But fundamentally, a law and a theory are essentially the same thing. The only difference is the strength by which the evidence supports it. Chemists study and describe the behavior of matter and energy in three different forms. The macroscopic domain is familiar to us. It is the realm of everyday things that are large enough to be sensed directly by human sight or touch. Baseball bats and baseballs and glasses of water and All of that is in the macroscopic domain. 2. The microscopic domain. It's almost always visited in the imagination. Micro also comes from Greek and means small. Some aspects of the microscopic domains are visible through a microscope. So this is saying two things. It's calling the microscopic domain the what you see in a microscope, but it's also going beyond that. What chemistry deals with is molecules and atoms. Under most conditions, they cannot be visualized. There are some scanning, tunneling microscopes that can see bumps of atoms on metal surfaces, but for the most part, these things that we deal with are so microscopic that they will never be seen directly by light microscopes. Then there's the symbolic domain, which contains the specialized language used to represent components of the macroscopic and microscopic domains, such as chemical symbols. So when we write chemical equations such as 2H2 plus O2 goes to 2H2O, then that is the symbolic domain. So these H's represent hydrogen atoms. The oxygens represent oxygen atoms, and the O2 represents the oxygen molecule, and the H2 represents a hydrogen molecule. So that is the symbolic domain. So here is how the scientific method is seen to work. Is you have observation and curiosity. These are the facts. From the observations, you make predictions, and then you perform an experiment or make more observations, and you keep going. If the results are consistent with prediction, then you have to decide, are we a theory or are we a law? And they're essentially the same thing, but in either one of them contribute to the body of knowledge we consider to be closer to the truth. Okay, let's read the caption. It says, the scientific method follows a process similar to the one in this diagram. All the key components are shown in roughly the right order. Scientific progress is seldom neat and clean. It requires open inquiry and the reworking of questions and ideas in response to findings. Okay, here we've got water in 3 different forms, and we're looking at it on the macroscopic scale. And over here we're looking at it at the microscopic scale, and over here we're looking at it at the symbolic scale. So A, moisture in the air, icebergs, and the ocean represent water in the macroscopic domain. B, at the molecular level, the microscopic domain, gas molecules are far apart and disorganized. Solid water molecules are close together and organized, and liquid molecules are close together and disorganized. And then C, the formula H2O symbolizes water, and the G, the S, and the L symbolizes its phases of gas, solid, and liquid. Note that clouds are actually composed of either very small liquid water droplets or solid water crystals. Gaseous water in our atmosphere is not visible to the naked eye, although it may be sensed as humidity. Okay, we're beginning section 1.2. phases of matter. Describe the basic properties of each physical state of matter, solid, liquid, and gas. Distinguish between mass and weight. Apply the law of conservation of matter. Classify matter as an element, compound, homogeneous mixture, or heterogeneous mixture with regard to its physical state and composition. Define and give examples of atoms and molecules. Okay. Anything in bold, try to remember, matter. Anything that occupies space and has mass. The three most common states or phases of matter are a solid, which is rigid and possesses a definite shape. A liquid flows and takes the shape of its container. It also has a definite volume. And a gas takes both the shape and volume of its container. And this are pictures to show this. Solid has fixed shape and volume. Liquid takes the shape of container, forms horizontal surface, has fixed volume. Gas expands to fill the container. The three most common states or phases of matter are solid, liquid, and gas. There are actually two more that are not really going to concern us in this class. One they mention in these slides, which is plasma. The other one they don't mention, and it would be called Bose-Einstein condensate. Plasma exists at a higher temperature than gas, and Bose-Einstein condensate occurs at very cold temperatures with very specific kinds of atoms, and it's too much to go into. But plasma, you do encounter this. If you're a welder, they do have what they call plasma torches, which send out a gaseous state of matter that contains electrically charged particles. And if you, I don't recommend that you look at the sun, but if you consider the sun also contains in its outer layer gaseous state of matter that contains an appreciable amount of electrically charged particles. That is the bright thing that we're looking at in the sun. We will probably, within your lifetime, be using electricity from fusion reactors. And fusion reactors fuse hydrogen nuclei to make helium nuclei and liberate energy. And they will use plasma. And it's much like the same process that goes on in the sun. So that's that for plasma. That's a plasma torch. Can be used to cut metal. Mass. Well, they don't say it here, but mass is measured by inertia, by the reluctance to move something, to accelerate something to higher speeds. It's a measure of the amount of matter in an object. Now, on the Earth, the gravity is more or less the same everywhere on the surface of the Earth, about the same. And we use the force of gravity to measure how much substance we have. But technically it's a weight. Weight is a force, a downward force due to gravity. And if you go to situations that have different forces of gravity, like you're in the wall of death centrifuge at a circus, or if you're on the moon, then your weight is different than it is naturally on the Earth, but your mass is no different. So the force you exert on the ground depends on your mass and the acceleration of gravity. So they are different things. The English system of measurement uses pounds as a measure of weight. Well, the more scientific metric system uses kilograms as a measure of mass. Anyway, it's important to distinguish the two. An object's mass is the same on Earth and the Moon, but its weight is different on the Earth and the Moon. Okay, here is a law of science. It's our first law that we're going to commit to memory, and it's the law of conservation of matter, which means that under laboratory conditions, we never destroy matter. Now, admittedly, it changed. Einstein was able to demonstrate that energy equals mass times the speed of light squared. And that's true. But matter is neither destroyed nor created from energy under normal circumstances here on the Earth. It is part of the fusion process that generates heat and light from the sun, but it is not part of what we're going to be dealing with here in our course. What this basically says is that if you've got a beaker of chemicals and you do something to it, all the mass of all those chemicals are going to be somewhere. Now, you may have boiled off some chemicals. You may have had a gas generating reaction that boiled off carbon dioxide. But we assume that whatever mass is lost was lost to the air, because if you did a much more careful analysis, you would find that the mass that was there will always be within a closed system. This is true for both chemical and physical changes. So chemical changes would be putting Alka-Seltzer into water and it bubbles up, and physical changes such as the boiling of water. The mass of what you start with never goes away from the universe. It may go away from your beaker, but it's not going to go away from the universe. Okay, the mass of beer precursor materials is the same as the mass of beer produced. Sugar has become alcohol and carbonation. And in the other case, case B, you've got a lead-acid battery. On the left, you have the charged battery, and on the right, you have the discharged battery. And so it's saying the mass of the lead oxide plates, and sulfuric acid that go into the production of electricity is exactly equal to the mass of lead sulfate and water that is formed. An element is a type of pure substance that cannot be broken down into simpler substances by chemical changes. The known elements are displayed in the periodic table. There are more than 100 known elements. 90 of these occur naturally. 24 or so have been created in the laboratory. I could at this point pull up a periodic table of the elements, but we're going to see this all course long on the, hopefully it's going to be on the on the wall of the lecture room, and if it's not, it's going to be available. Anyway, Uh, uh, I would say there are approximately 90 uh, elements occurring naturally. There are a few, technetium, um, astatine, francium, that do not occur naturally or to any great degree. So um, before you get up to uranium. So we're going to know the periodic table. Now, what makes it an element is that it's a type of pure substance that cannot be broken down into simpler substances by chemical changes. It can combine with other pure substances and change, but it cannot be broken down. Okay, so here we are going to define a pure substance. Pure substances have constant composition. Okay, so a pure substance is like sugar or table salt. If you find sucrose, pure sugar, someplace in the world, it has the same composition as sugar found elsewhere in the world. Sucrose, table sugar. Same thing with table salt. Table salt is the same composition anywhere you find it in the world. Now, a subset of pure substances is an element. Elements are pure substances that cannot be broken down into simpler substances by chemical changes. A very simple experiment done with water is electrolysis, where you generate hydrogen and oxygen from water. Well, that water was broken down by chemical changes into hydrogen and oxygen, so it was not an element. However, as it turns out, the oxygen and hydrogen cannot be broken down farther, and they are elements. Other examples of elements would be carbon, gold, as it says here, oxygen, aluminum, and others that you may encounter during the day. When you look at the periodic table of the elements, you'll find words that you already know, like iodine and chlorine, or neon, like neon lights. These are all elements. Okay, compounds. Compounds are pure substances that can be broken down into simpler substances by chemical changes. They consist of two or more types of elements chemically bonded. Examples are H2O, water, C6H12O6, which is glucose. Now that's not the same as sucrose that you have on your kitchen table. This is also known as dextrose. It's a major component of syrups like Karo syrup, corn syrup. And AgCl. Believe it or not, Ag means silver, and the Cl means chloride. The reason why Ag means silver is it's based on the Latin for silver, which is argentum, the same thing for which the country Argentina is named for. And finally, the properties of compounds are different from the uncombined elements making up the compound. Okay, so a compound is different from its elements. So, sodium chloride, table salt, is a perfect example, with sodium being a metal that if you were to expose it to the air and throw it in water, you'd get a fire. And chlorine, which is used as a war gas that destroys people's eyes, nose, and throat, and kills them, destroys their lungs. But you allow the sodium to burn in chlorine, and you get this fine powder of salt. And this salt our bodies actually need and tastes good. Okay, here we've got mercury oxide, or mercury 2 oxide. When it's heated, it decomposes into mercury and oxygen. So this is an example of a decomposition into the elements of mercury and oxygen. A mixture is composed of 2 or more types of matter that can be present in varying amounts and can be separated by physical changes. Okay, let's talk about iced tea in the glass with ice. Okay, you've got you've got 2 mixtures here. You've got a mixture of water with sugar and tea bags, what comes out of the tea bags. And you've got ice in the iced tea. Now, there are various ways you can physically separate the ice by just running it through a strainer. And then you can separate the water from the other parts of that compose iced tea by distillation, by boiling it and driving the water to steam and then recondensing the steam. So iced tea is an example really of 2 types of mixtures that we're going to talk about. Evaporation is an example of a physical change. There are 2 types of mixtures: homogeneous mixtures and heterogeneous mixtures. Homo means same and hetero means different. And so this means that you've got gen usually means birth. So it's born the same and born differently. Okay, a homogeneous mixture exhibits a uniform composition and appears visually the same throughout. So you can think of this as the tea, the liquid tea part of iced tea. That liquid tea is a uniform composition. It's the same brown stuff all the way through. It's brown sweet stuff, and it is a solution. A heterogeneous mixture has a composition that varies from point to point. Okay, so once you put the ice in the iced tea, now you have a heterogeneous mixture of that original homogeneous mixture and ice. So as you move in a little submarine through there, you can hit the chunks of ice. Those are of one composition, and you move out into solution, and it's a different composition. So that would be a heterogeneous mixture. Oil and vinegar salad dressing is a heterogeneous mixture because its composition is not uniform throughout. If you look very closely, even something like mayonnaise on a microscopic level is composed of oil droplets and water-based mixtures outside of that oil. A commercial sports drink is a homogeneous mixture because its composition is uniform throughout. So here they've taken Gatorade, and that's I don't think they really took a micrograph of Gatorade, but they're representing it with that solid block of color. Okay, so here's a flow chart. You got some matter in front of you. Does it have constant properties and composition? That means if you find it anywhere, so let's take iced tea. Does it have constant properties and composition? Well, is iced tea, sweet iced tea, is that going to be the same in IHOP as in Outback? No, it will not. Is it, but now the sugar in the bowl, is it going to have the same composition at IHOP as Outback? And the answer is yes. So the sugar is a pure substance, but the iced tea is a mixture. Okay. Is it uniform throughout? Well, if you ask it to have it without ice, the answer would be yes, and you would have a homogeneous mixture in your glass. If, on the other hand, you asked for the ice of iced tea, and you had ice and tea in your glass, it'll be heterogeneous. So the answer is no. On the other hand, your sugar, bring it over here, can it be simplified chemically? Well, it turns out you can burn sugar, and it turns into other substances. It turns into carbon dioxide and carbon and water, by the way. If you heat it up, you can actually measure the water driven off. Can it be simplified chemically? Yes, it can. That sugar is a compound. It turns out even salt can be simplified chemically, but it's not easily. And of course, higher temperatures than you would normally want to put on it. Or it could be electrolytically separated. So salt is also a compound. But carbon, if you had a piece of charcoal, can it be simplified chemically? Well, it turns out it cannot. Carbon is carbon, and it would be an element. Depending on its properties, a given substance can be classified as a homogeneous mixture, a heterogeneous mixture, a compound, or an element. So you take I'm going to describe this a little bit differently than this, and then I'll read what this says. But if you take a thing like a piece of wood, and you keep cutting it. You cut it in half, and you cut it in half, and cut it in half, and cut it in half again. You still have a little piece of thing that would still be wood. For a pure substance, now it turns out wood is not a pure substance. Wood from birch is different from wood from pine, and so forth. But let's say a sugar cube. The smallest thing that is still that substance is a molecule. And that's true of all substances. Now, molecules, they can consist of a pure element. They can consist of two or more elements. So if we take an element like carbon, and we keep cutting that carbon up into smaller and smaller pieces, the smallest thing that is still carbon is an atom. So now I'll read this. The smallest particle of an element that has the properties of that element and can enter into a chemical combination is an atom. It was first proposed by the Greek philosophers Leucippus and Democritus in the 5th century, and later in the 1800s by John Dalton of England. Now, an atom can be a molecule. A molecule is the smallest thing that is still a pure substance. And if that pure substance is an element, well, some elements like oxygen have molecules composed of one element, so they'd be O2. But then there are things like neon and argon and helium, that their molecules actually consist of one atom. So I disagree a little bit here with OpenStax. Molecules don't have to consist of any more than one atom, although they frequently are two or more atoms connected by strong forces known as chemical bonds. But you take a pure substance like silver or gold, the smallest thing of that metal is still is an atom, and it's the molecule of that metal. Okay, this photograph shows a gold nugget. A scanning tunneling microscope can generate views of the surface of solids, such as this image of a gold crystal. Each sphere represents one gold atom. Okay, so this is a case where a kind of microscope can see atoms in a solid metal substance. Most of the atoms that we're going to be dealing with, most of the situations that we're going to be dealing with do not yield to being looked at with a scanning tunneling microscope. Okay, so here we're going to the macroscopic, microscopic, and even more microscopic domains for cotton. Cotton is a representation of pure cellulose. It forms fibers. It's generated naturally on a plant that it's called a cotton boll. And we're zooming in. This is the optical microscope. This is the electron microscope. And this is what we know to be in there for where you can see the atoms. Of course, we don't have a microscope that can see this, but it can be constructed. It actually can be inferred from X-ray scattering. And this is what we know to be in cotton to make the structures that it has. And here we focus in on just one unit of cellulose. So these images provide an increasingly closer view. A cotton boll, that's what they call the cotton as it comes off the plant. B, a single cotton fiber viewed under an optical microscope, magnified 40 times. An image of cotton fibers with an electron microscope, much higher magnification. And D and E, atomic level models of the fiber with spheres of different colors represent atoms of different elements. Of course, black represents carbon, white represents hydrogen, and the red represents oxygen. Only a few elements exist as individual atoms. Well, those would be the noble gases: helium, argon, krypton, neon. I would say most of the metals also exist as individual atoms or as extended metals. Okay. Most elements exist as molecules in which two or more atoms of the same element are bonded together. Well, all the other gases other than the noble gases exist as diatomic molecules. And then you have things like sulfur and phosphorus, which do form molecules and may actually be liberated into the gaseous state. Many molecules consist of two or more atoms of different elements. And atoms in all types of molecules move as a unit. I'm having a hard time understanding what that means. Later, we'll get into what's inside of atoms, the electrons, protons, and neutrons. And of course, they all move together as an atom. So maybe somebody can enlighten me as to the real meaning of this thing other than Captain Obvious that an atom moves as an atom. Okay, here we have hydrogen, oxygen, phosphorus, sulfur, water, carbon dioxide, and glucose. So this is how chemists think of these things, as little balls that are connected to one another. We also think of the connections here as sticks, although that's not this particular representation. And we call the sticks between them, we would call bonds. So here it says, the elements hydrogen, oxygen, phosphorus, and sulfur form molecules consisting of two or more atoms of the same element. The compounds water, carbon dioxide, and glucose consist of combinations of atoms of different elements. And of course, they chose here what we normally think of as a liquid, a gas, and a solid. The decomposition of water shown at the macroscopic, microscopic, and symbolic levels. The battery provides an electric current that decomposes water. At the macroscopic level, the liquid separates into the gases, hydrogen on the left and oxygen on the right. Now, this thing doesn't go up very far, and it doesn't go up far enough, but suffice to say that the column of hydrogen before you get to the meniscus is twice as big as the column of oxygen before it gets to its meniscus. Symbolically, this change is represented by showing how liquid H2O separates into H2 and O2 gases. And here's H2O and H2 and O2. A fuel cell generates electrical energy from hydrogen and oxygen via an electrochemical process and produces only water as the waste product. So this is exactly the opposite of electrolysis. We're feeding oxygen and hydrogen into this thing. It's producing water, and we're getting electrical power out. A cell phone, it says here, almost 1/3 of naturally occurring elements are used to make a cell phone. So you've got polymers and metals for the case. So polymers, they're going to be hydrocarbons. This says atactic butylstyrene. That's carbon, hydrogen, and maybe nah, it's only carbon and hydrogen. And metals such as aluminum, iron, and magnesium. It's got processor components like silicon, and then the wires connecting them with copper, tin, and gold. And then the silicon is doped with various things, perhaps yttrium and gadolinium. The glass on the front is silicon oxide with a lot of other things in there, aluminum and sodium and potassium. It says strengthened by the addition. I beg to disagree. This glass is run through a molten salt bath that exchanges some of the ions on the surface that actually create a skin that's tighter. Then battery components, they call them lithium-ion batteries because they contain lithium, and they have other metals such as cobalt, iron, or copper. So the modern-day cell phone, an awful lot of chemistry has come together to make that magical thing in your pocket. Okay, we have gotten to section 1.3. This is where we will stop today on the first lecture. Please, if you have any questions that occurred during today's lecture, please bring those to class. I will be happy to answer your questions. We're going to look at the problems in the back of the book, and we will go through those problems and try to answer them. Thank you very much for listening, and I shall try to get out of this without too much problem. Goodbye.